Hi, everyone. Thanks for tuning in. My name is Luis, and I'm a lecturer at the School of Applied Mathematics at the Getúlio Vargas Foundation in Rio. And this is going to be joint work with Remco Boekach from the University of Auckland in New Zealand. And today, I thought I would talk to you a bit about how we measure mixing for MCMC when the target is a phylogenetic target. So some of the parameters of interest are phylogenetic trees. In particular, I'll be focusing on binary variables, clade indicators. So before I start, I should tell you to go watch Andy McGee's excellent presentation. He sets up a bunch of background that I won't be doing here. So this presentation has been designed to dovetail off of his. But what I will say is that trees are hypotheses about the world, about evolutionary history. So, you know, biologists are usually very quick to pick up on what the true tree or the correct tree is here, but mathematicians and statisticians usually struggle a little bit. So you might think this is the correct tree, right? That gorillas and chimps are closer to each other than we are to them, but that's, well, not true, right? The correct tree is this one, right? And what this tree does is that it tells you a story, and the story is that there once was a creature that was the ancestor of gorillas and whatever the ancestor was of humans and chimps. And then that lineage split in two, and then the ancestor of chimps and humans, also split in multiple lineages, that one of which culminated in Homo sapiens, which is, well, what we are. This tree then tells you a story, and if you attach length to these branches, you can tell not only a qualitative story, but also a quantitative one. So meaning you can say not only what the relative timing of these split events was, but also the absolute timing in terms of calendar units. So this is a way of telling an evolutionary story in real time, right? And this is sort of what we are interested in doing in phylogenetics. So here I've written the phylogenetic target distribution, so we can have a little look at what it looks like and what the complexity is. So here, B is the branch lengths, which is a fixed, potentially high dimensional vector. Omega are a bunch of parameters of interest like mutation rates, migration rates, population sizes, all sorts of things that we would like to know from genetic data by conditioning on the phylogeny. And T here is the topologies, the branching order that I showed you before. I am aware that we usually don't write the normalizing constant because we usually don't need that to sample from the target. But here I did this intentionally to sort of try and convey the complexity of the problem, right? This is a very hard problem because after you integrate over branch lengths and parameters of interest, you'll still have to sum over all of the trees. And it's this discrete component that obstructs exploration, right? That gets in the way. Right, so how do we look at this discrete component in a productive way when we have, well, draws from a posterior, want to know if those are good draws? Well, one of the things we can do, not only in phylogenetics, but in general, is look for a lower dimensional projection, right? And here, there's a very broad class, or a very natural class, should I say, of projections, which are clades, right? So here I'm showing you, well, two families of clades. These are disjoint clades, right? So clades are basically subtrees, and these are disjoint. But clades can also be nested, right? So here, red is nested within yellow, which is in turn nested within blue. But these subtrees, these clades, these partitions are a very natural thing to look at, right? But why? Why are we looking at clades? Well, first of all, there's a huge dimensional reduction, right? So little n here is the number of leaves in the tree, and in modern analysis, this could range from a few dozen to a few hundred up to some thousand leaves. So this is a humongous number, right? It's absolutely astronomical, doesn't cover it, but it pales in comparison with this number. So this is a double factorial, meaning that the size of tree space grows super exponentially with the number of leaves, right? So looking at clades does give you a substantial dimensional reduction, even if that's still a high dimensional space. Clades are also interpretable, right? So if you come back to the story I told you about humans and chimps and gorillas, the clade human chimp, that's directly interpretable. So if I'm looking at a procedure distribution and I look at the frequency of that clade, this tells me something about evolutionary hypotheses. So for instance, the evolutionary hypothesis that humans and chimps evolved, well, later than humans and gorillas, for instance. Under some simplifying assumptions, these clades are going to be nearly independent. Technically, they're never independent. Their correlation is either negative or positive, but never zero. That's because they are partitions, right? So they are tied in that particular sense. But under some simplifying assumptions, you can make them virtually independent. And also, the frequency of the clades is known in closed form for certain priors. So there are certain manipulations we can do with clades that we couldn't potentially do with other lower dimensional projections. Right. So what's the setup here? Well, the setup is I'm going to have an indicator for a particular clade, whether that clade is present in a tree that was drawn at the ith iteration, and each tree will have a fixed number of clades. And this will lead to a matrix that has big J columns and big M rows, where M is the number of draws. So each row is a draw, and I'm going to say whether that particular Jth clade is there or not, right? So this is the general setup. And the kind of data you would be looking at then from MCMC would be something like this, right? So either the clade is zero, right? Or either it's off or it's on, and then it switches back and forth along the chain, right? Sometimes it will just go to one and get stuck there, or go to zero and get stuck there. And that tells you something about, you know, both mixing and what the posterior probability of that clade is. Cool. So, all right. So we have a binary process, right? A binary stochastic process. And what happens if we try and model that with a Markov chain, right? And so this is precisely what we're going to do here. We're going to pretend that that process is a Markov chain in 0 and 1. And in particular, we're going to reparameterize the model slightly in that we're going to parameterize it in terms of a marginal success probability or frequency, and a transition probability that controls the flipping rate or the switching rate, right? So how fast that chain is changing states. If that's, you know, in that setting, we can estimate P and alpha in closed form, right? So we first estimate P by maximal posteriori or maximal likelihood, and then we estimate alpha conditional on P. And I have some results that show that works really well. It's not surprising at all. There's a lot of data. I'm not going to show that here, but it works well. Cool. So that's our model. So what having an explicit model buys you is that you can derive the distribution of a bunch of potentially important quantities in closed form. So with that model, we know what the distribution of occupation times is. So, you know, occupation time is how much time you spend at, let's say, the one state, right? We can also estimate, or we can also derive the distribution of states transitions. So whenever you change from 0, 1 or 1 or 0 in closed form. And we can also compute the effective sample size in closed form, right? It takes this lovely little form here. Right, so that's what having an explicit model buys you. A second thing that it buys you is that then if that is really the model, then you can create some measures of performance that are custom made for that model. So here, for instance, I'm taking, so Y is the process where I only count the transitions, right? So that is also a two-state Markov chain. We proved that in the paper. By the way, I'm not claiming ownership or novelty with any of these results. I appreciate these might have been proven before, but I looked in all of the books and I couldn't find them. So I re-derived some of these results, and I would be very glad if someone pointed out to me where I could find, you know, these results, something like this, right? I'm not claiming ownership here or novelty. But anyway, we can take the average number of transitions, the state transitions, and we can scale that by the maximal number under the model, right? And that, you know, the closer this is to 1, the more mixing you have, the closer to 0, the less mixing you have there. We can do a similar thing with alpha, so we can take the estimate of alpha and divide by the maximum it could possibly be for a given p. And this is a bit more model agnostic in that what I'm doing here with this delta thing is I'm taking the number of transitions observed in that particular binary string, and I'm dividing that by the maximal possible number, right? So this is model agnostic, but if you wanted, for instance, to derive a confidence interval for this quantity, you could simulate under this model and then, you know, via parametric bootstrap and get a confidence interval for this measure. They're all closed form and easy to compute. So how does that look in practice? Well, if I take a particular phylogenetic posterior and I look at independent versus dependent samples, and we can do that because we can fake phylogenetic MCMC. See Andy McGee's presentation for more details, but suffices to say that after I've sampled from a posterior, there are ways of approximately sampling independently from that posterior, right? So that allows us to run experiments like this, where we sample independently, then we look at the distribution of ESSs across clades, and it looks like this. So it's really close to nominal, right? Whereas when you sample from the posterior using regular MCMC, some clades perform well, some don't, and that's what you see there. So this is looking really cool. So what could possibly go wrong? Well, earlier this year, Luisa Fabretti and Sebastian Höhner published a preprint where they investigate precisely this issue, and they also have a way of generating a binary process with a pre-specified ESS, which is not necessarily Markov. So how does our method perform in that case? Well, like this. So purple here is our, you know, Markov chain based ESS, and here are popular methods for estimating ESS. So that's Stan, and then Coda, and Tracer is a popular phylogenetic software of which, you know, Luis and Sebastian have an implementation R. It's a package called Convenience. I highly encourage you to check that out. So what's happening here is our estimator is being fooled by their algorithm into thinking that the ESS is much lower than it should be. And we know that the true ESS is really this, because we can do this by brute force, by repeating the same simulation a bunch of times and computing the standard error of the mean in, you know, by brute force. So these methods are doing the right thing, and our methods doing completely the wrong thing. So what the hell is going on, right? Why is my lovely closed form little method not working? Well, it's not working because if you look at two binary process, one of which is a Markov chain, another of which is their simulation. Both of them have autocorrelation time 50. This is what you see. So red here is the Markov chain, and black is, well, their process. So both of these processes have the same ACT, therefore the same ESS, but the red process, the Markov chain, has way more states transitions, right? So when you look at that in real data, you're going to see way fewer transitions, and therefore your method, my method, is going to be fooled into thinking that's a very slow mixing Markov chain. Another way to see this is to look at the autocorrelation spectra in this case. So here I'm showing you the empirical autocorrelation spectrum, and here I'm fitting my Markov chain model there. And as you can see, for low legs, small legs, everything's working just about fine, but then it drops off way too slowly compared to the real data, right? So that will make it think, right, that the ESS is much lower than it should be. Okay. So what can we do to fix that? Well, one of the things we can do is we can devise a very expensive estimator where we estimate the autocorrelation time directly, non-parametrically, like we always do. And if it's bigger than, say, 1 or 2, then we just return the number of draws over the autocorrelation time as we would normally. But if it isn't, right, if it's closer to 1, then we compute P and alpha and we return the Markov chain based ESS, right? And I have some evidence that this actually works well. So because it accommodates super efficient binary processes that are sampling, faster than independent sampling. But it's also more expensive, right? So, swings and roundabouts, I suppose. The other thing we can do is we can use a log linear representation of the problem to compute base factors and test first order Markov chain against a second order Markov chain. And this gives us an idea of the adequacy of the Markov model, right? This is ongoing work. I mean, this is a very old technique, but it's for this particular application, I'm still ironing out the kinks. But this is something that we should definitely do, right? Is to test whether the model is adequate. A last idea that I would like to explore is the fact that, as Andy and his collaborators point out, trees are fundamentally multivariate objects, right? So considering each clade individually is probably not the right thing to do, right? So, but we can fix that by computing a multivariate ESS using that binary matrix we formed in the beginning. But what this figure is showing you is that we have to be a bit careful. So when we compute these covariance matrices, we do it in a numerically stable way so that the eigenvalues are never negative, right? So this is using RSCOV, right? And you see that some of the eigenvalues are negative when we know they shouldn't be, right? So when you compute the covariance matrix in a numerically robust way, the problem goes away, and therefore this can be computed, right? This is not an indeterminate form. Great. So to wrap up, assumptions are very useful, right? So if we could assume that the process is Markov, we could derive a bunch of things in closed form. They're cheap to compute, they're very accurate, but they do matter, right? So in this particular case, the Markov assumption was much too strong for certain processes, that some binary processes that people can generate. Our approach has the advantage of seamlessly accommodating antithetic, super efficient binary processes. So if you're facing an application where that's potentially present, our method will do the right thing and estimate ESS the correct way for you. And finally, the last idea I discussed is we could potentially compute a multivariate binary ESS that accounted for the correlation between the clades and gave you an overall idea of what's going on. So with that, I thank you very much for your attention, and I hope to see you at the workshop. Thank you.